What's going on, everybody? Mr. Diamond yet again, coming from the Diamond Layer, and we are going to be going over, get my cool pointer going, Section 2, Electrons and Configurations. This is Section 2 of Chapter 1 for my chemistry class. And we're going to still be talking about electrons. We're not quite to the radioactive stuff just yet, but we'll get there. Don't worry. I know people usually get super excited about that. Now, as we discussed, we know now electrons no longer fill nice, neat rings. This is due to their dual wave particle nature. They behave erratically. So instead of giving them rings, instead of giving them loops like the Bohr model of the atom, we instead say they occupy orbitals. And an orbital is an area that an electron can be found about 90% of the time. And it may be like, oh, whoa, Diamond, 90, that's 10% of the time unaccounted for. That seems like a really low number. And you're right. I don't know what else to tell you. You're right. It is like, it seems like an almost unreasonably large amount of information to just be like, well, yeah, 10% of the time it could just not be here. But it's kind of the best we can do. We're not going to talk about it a ton, but if you've ever heard of the Heisenberg uncertainty principle, that's the idea that if you try to measure something really closely, the act of measuring it will basically influence what you're trying to do. The same thing here. As we get better and better techniques to actually like look at electrons, the act of looking at them, because it involves light and because it involves like different machines and stuff like that are going to be emitting radiation and emitting all sorts of stuff, or they're going to be electronic, so they're going to have electronic signatures coming off of them. All of that kind of stuff is going to mess with it, and that's going to make it even harder for you to actually figure out what's going on. You can't tell if the electrons are actually in their natural state or if they've been influenced by the stuff around it. So you can get the location pretty good, but by that point, you've messed with everything else about it that you really only get the location. And you do the same thing with the speed. You can measure the speed pretty accurately, but once you get the speed measured really accurately, you can't really tell like the location the electron is going. So 90% of the time is actually good enough for our purposes. You could think of it kind of like, especially during Rona time right now, me saying like, well, I don't know where you always are, but I could take a guess that you're at school, at home, and if you have a job, at work. One of those three places is probably going to account for your location most of the time. Now, sure, you're going to be driving between them at some point. Sometimes you might be sneaking out to do a cheeky visit your friend and break quarantine, and then don't do that, though. That's bad. You shouldn't do that. Or you may be going to the store or something like that. But 90% of the time, you're in one of those three locations. And that's kind of what orbitals are for electrons. They're basically the area they normally hang out in. It's their stomping grounds where they normally chill. And every orbital can have two electrons. They can fit two of them. Two electrons can fill each orbital, and there are 4 types of orbitals. This is going to definitely be the first chapter where I know some people felt really rough about last chapter, but like I kept pointing out, it was the first chapter that you guys have to deal with. You don't know what to expect kind of question style. You probably realize that I expect you to have a deeper level of knowledge of some stuff, and just memorizing doesn't necessarily help you. But this chapter is going to definitely start down the path of there is a lot of stuff that you really want to make sure you're paying attention to, and you want to make sure you understand, not just think you understand. So 2 electrons can fill every orbital, and there are 4 types of orbitals. There are s orbitals, which are sphere-shaped, and there's 1 possible orientation. So because there's 1 possible orientation, you can have 2 total electrons in an s orbital, or in a sphere sublevel, basically. Sublevel is another term you're going to hear. I'm not going to get super specific on my terminology for you guys. If you take organic chemistry, we'll go into more detail about this. But basically, a sphere, if I try to not bump my mic that I've already dropped and damaged, if you have a sphere, wait, I have a sphere around here. Okay. If you have a sphere, for example, a tennis ball, I'm going to try to get my light angled better. How's that? Ooh, that's much better lighting. Why didn't I do that in the first video? So if I have my sphere, no matter how I rotate the sphere, no matter how I turn it, it is always a sphere. It always takes up the same location if I were holding it the same 3D space. It's always a sphere. And it looks like a white ball of energy. It's actually a tennis ball. So get closer, you can see. I'm not like manipulating matter on the fly right now. Don't worry. So there's only one possible way it can fit, which means you can only fit 2 electrons. Now, why does orientation matter? Well, when you get to p orbitals, are dumbbell shaped. They kind of, oh man, don't have any good visual aids around here. Well, piece of paper it is. Scoot all this garbage out of my desk out of the way. Get that out of the way. Get that out of the way. Get that out of the way. There we go. And there is going to be pictures later on in here if you want to see better looking ones. I really hope my camera's not mirrored. Yeah, moment of truth. Nope, camera's not mirrored. Cool. So the one on the left for you guys is an s orbital. It's just a sphere. A p orbital is dumbbell shaped. So it's got these like lobes that are kind of like jutting down, and there's kind of an empty area in the middle of them. So because there's an empty area in between it, you can actually rearrange it. So the sphere, again, if I rotate it one direction, it still takes up the same location. It's still occupying the exact same space as I rotate it. It's not changing anything. But the dumbbell shape, and I'm going to oversimplify it and use my pen instead. If I can hold my pen up and down, but I can also hold my pen left to right, and I can also hold my pen in and out. There's an X, a Y, and a Z axis that can be occupied by a p orbital because it's dumbbell shaped. And because of that, there are 3 possible orientations you can position it. All 3 of those orientations can hold 2 electrons. 3 times 2 is 6 total electrons that would be on a p sublevel. There could be 3 types of possible p orbitals on one level. Then there are d orbitals. I could sketch the shape, but we're getting to the point where I don't expect you to really be able to like draw the shape. I could have you draw on the test an s and a p orbital. In fact, that would be a pretty good test question for a short answer, is just sketch a p orbital or all possible s and all possible p orbitals, and you would just have to do a circle and then a little up and down, a side to side, and like an in and out, and label that one's x, y, and z. Hint, hint. But d orbitals and f orbitals, I won't expect you to know. D orbitals are double dumbbell shaped, and basically they get so complex that you can actually orient them 5 ways. Instead of just rotating them in x, y, and z, you can actually kind of tilt them and angle them in different directions. So you can fit 5 of these d orbitals on one level, on a d sublevel. So that'll give you 10 total electrons. And then finally, f orbitals are fancy or flower shaped. They are very complex. You can squeeze 7 of them on one level, and that will be 7 times 2, 14 possible electrons. Now I'm hoping this next slide is the pictures that are better than mine. So yeah, here are the better pictures for it. So spheres, you've got this one shape right here. It's just kind of a circle. And again, as you rotate that sphere, nothing is going to change. For p orbitals, we've got an up and a down, we've got an in and an out, and we've got a left and a right. So we've got 3 possible orientations. Then for d orbitals, these are kind of 2 possible ways you could think about it. Because again, remember, these are not like solid. This is not a solid sphere. This is a cloud where an electron could be found 90% of the time. This is an orbital. So this is, thought my cat was freaking out. I apologize. This is a sphere where 90% of the time you could find a pair of electrons, or only one if it doesn't have both of them in there yet. But there could be a pair of electrons in this sphere somewhere 90% of the time. It could also be like way over here, or over here, or over here, or in a different level. That other 10% of the time, we don't know. P orbital is the same thing. This is not a solid shape. This is a cloud, a fuzzy area where the electron could be here, or here, or here, or here, or here. It's less likely to be here at the very middle because that's the area that the s orbital is. But out here on these kind of bulbs on the end, you could find both electrons on this side or both of the electrons on this side, one on each side, whatever. The 2 electrons will be somewhere in this area. Same thing with this one, same thing with this one. The d orbital gets way more complex. You could also think of it as a double dumbbell because it's got 1, 2, 3, 4 lobes. We can arrange those 4 lobes in 5 possible configurations. And then same thing, you'll notice that they don't line up exactly on the x and the y axis or the z axis. That's because that's where the p orbitals are. So they're trying to fill in space is their goal. They want to try to fill up space that isn't occupied. And then finally, f for fancy or flower shaped. You've got 1, 2, 3, 4, 5, 6 going on each of them, or depending on how you look at it, you might have 1, 2, 3, 4, 5, 6, 7, 8. It just depends on which of these configurations you're looking at. But you've got a ton of stuff, and there is 1, 2, 3, 4, 5, 6, 7 possible configurations that you can have. And so in those 7 configurations, each one of these could have 2 electrons, and it could be anywhere in any one of these bulbs because, again, they represent clouds of probability. They're locations you can probably find them. Now, conveniently, you guys get a periodic table on every test, and the periodic table actually tells you most of this information. If you look at the periodic table, the S block, there's 1s, 2s, 3s, 4s, 5s, 6s, and 7s. There's 7 total s orbitals that could be found on an atom, or up to 7. And each one can hold 1, 2 electrons. Now, helium's way over here, but remember, helium and hydrogen go together. Most of the time, it's easy to assume hydrogen goes here, but in this case, it's actually easier to assume that helium comes over here. So 1, 2, and the first elements are s because s is the first type of orbital that gets made. And then there are up to 7 of them. And then you can mentally remember that if you break the table up like this, you can just divide the number of elements in one row by 2, because again, every orbital, 2 electrons, divide it by 2, and that will tell you how many possible orbitals there are. So if you remember, this is S block, there is 2 electrons, 2 divided by 2 is 1 orbital. So again, S orbitals can hold 2 electrons because there's only one possible configuration for it. You can only have 1 s orbital. But for p orbitals, a p sublevel, they start on energy level 2. Notice this is 1s and then this is 2s. If you remember, this is p block. This starts on 2. You can count 1, 2, 3, 4, 5, 6. 6 divided by 2 is 3. There's 3 possible configurations of a p orbital, so you can have up to 6 total electrons. So this has gone 1, 2. D block is 3. It starts down here. Now, this is where people can start getting confused if you're not already. I know this is a lot, but we're going to practice this a lot in class, and there's going to be a lot of worksheets about this. Don't worry. This is on the 4th row, 1, 2, 3, 4. And like this one was on the 2nd row, so it makes sense that it would be 2p. This is on the 4th row, but it starts on 3, and that can be kind of confusing. I just remember that it's SPDF 1, 2, 3, 4, SPDF 1, 2, 3, 4, SPDF 1, 2, 3, 4. I do that kind of zigzag shape, and I just remember SPDF 1, 2, 3, 4. And then as long as you kind of just put a little 3 right there when you get your blank periodic table, it usually helps kind of remember that. The reason for it is because this d orbital, this shape, if I click back here, is like massive. It is much bigger than just these 2 simple ones right here. So on the first energy level, which we'll talk about later, energy levels are basically how far away from a nucleus you are. When you're really, 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 really close to a nucleus, you can only fit a circle. There's not a lot of space around it. But as you go further out, you can start fitting more and more complex things. P orbitals can be added not when you're in the first energy level, but when you're in the second energy level, when you've moved out slightly. D orbitals can get added to the 3rd energy level, but they're so massive and they take so much energy to build that they actually don't get added until after you've already built the 4s orbitals. And then F block is even worse. F block is 14 elements. 14 divided by 2 is 7. So you can have 7 configurations. And then F block will actually fit in right here. So it's going to be on level 4, but it actually is on the 6th row. So again, just remember SPDF 1, 2, 3, 4. SPDF 1, 2, 3, 4. Now, sometimes in science, it is necessary to account for all of the locations of all of the electrons in an atom. And to do that, we use an electron configuration. It is a summary of the specific locations and energy levels of each electron. If you kind of remember the Bohr model, which we said was useful because it put the electrons on energy levels, and that was how it validated or how it kind of confirmed the idea that electrons could orbit around here without collapsing in. Well, these are energy levels. You've actually already done this. You've put electrons on energy levels before. So for example, it would be the first energy level. We just said energy levels can only fit, the first one can only fit an s orbital, and an s orbital can hold how many electrons? It can hold 1, 2. The second one is 1, 2, 3, 4, 5, 6, 7, 8. And if we click back and look at the slide, there's 1, 2, that's an s orbital, and then 1, 2, 3, 4, 5, 6, that's a p orbital. And you might be thinking, wait a minute, so that's the octet that we're talking about. And if you didn't make that connection, then I'm telling you that. That's actually why you have the octet rule. The octet rule comes from needing to fill up the s orbital and the p orbitals. Those are always the outermost, the valence electrons, so they always get to be, need to be full, or atoms want to have them full. So there are 3 rules that govern how these electrons are going to be arranged. And these are like a really good candidate for a matching question on this test, because they're just 3 things that I can kind of show you, give you the name, and then give you what they are. I would not expect for me to make you like recite them, just like regurgitate them completely on the test. So rule number 1 is the Aufbau principle. Electrons will occupy the lowest energy level first. I think of it as water. Water always goes to the lowest point. You don't fill a glass from the top down. You fill a glass from the bottom to the top. And that will give us a pattern for how electrons fill. If we know that electrons always go low to high, and we can predict which ones are lowest and which ones are higher, we can find a pattern that will pretty much always work. And we can kind of follow that pattern and know that that's where electrons will go. Now, if you take organic chemistry, we'll talk about cases where this doesn't happen. But most of the time, it works out really nicely for us. The second rule is the Pauli exclusion principle. No 2 electrons can have the same location. Think of where you're sitting right now. No one, or you're standing, I guess, or you're looking on your phone, or you're, I don't know, you're doing this at the gym. If you're doing that, like, good for you. Working out's hard, man. I've been trying to do it, and man, it's tough. But if you think of like me, I am in a chair right now, sitting in my living room. And while I'm in this chair, there's nothing else that can be in the same location as my butt. Now, someone could sit on me. My cats love to do that all the time, but none of them are close, thankfully. I mean, I guess not thankfully. You get to see my cats. But nothing can be in the exact same location as me. And so because no 2 electrons can have the same location, or because nothing can be in my seat, it makes sense that the same thing would place for electrons. Nothing can be in the same place as another electrons. Even if 2 electrons are in the same orbital, because again, and I cannot stress this enough, that's why I keep repeating it, every single orbital, which is just a cloud of probability where an electron can be found 90% of the time, can hold 2 electrons. Even though those 2 electrons are in the same orbital, they have to be different somehow. And the way that they're different is by their spin. One of them is an up spin and one of them is a down spin. You can kind of think of it as one goes clockwise and one goes counterclockwise. So I don't know if I'm doing them opposite directions. Whatever. But they're basically going opposite directions so they can avoid each other pretty much. They're not in the same place. And then finally, Hund's rule. Hund's rule says that electrons will fill all available orbitals once before they pair up, which will, for us, will look like every line should have 1 arrow before you give any of them 2. And I can already hear some of you, especially those of you who are digital, going, every line should have 1 arrow. What the heck does that? Don't worry, I'm going to have a separate video of me actually going through the examples of this, because this video is already going to be pretty long, but I'll get to that. Don't worry. Because of these 3 rules, we not only know the kind of general location of orbitals, like we can say, oh, it's like a 2p, or it's a 4s, or it's a 5f, or whatever. We can actually predict where every single electron is. They can't be 2 electrons in the same place. Everything gets half filled before it gets fully filled, and we know it goes low to high. So those 3 rules let us figure out where every single electron must go, assuming that everything is working according to plan. So not only do we have the S block, the P block, the D block, and the F block, but we can know that this is 1s1, 2s1, 2s2, 2s1, 2s2, 2p1, 2p2, 2p. We can go through this whole thing and have the entire thing labeled. And again, it's convenient to write helium for this one, so it just makes more sense in this example to be over here. But we don't just know that this is the 1s. We also know we can give specific numbers for each of them for each of these locations. Now, I might get into this a little bit more later on, but this is a good time to mention this. This will always work the exact same way every single time. For this class, we'll go into a little more detail if you take an advanced chemistry or an organic chemistry, but like this pattern is just always the same. Like you can just keep going, and if you know kind of the idea of the pattern and how it goes and how it bounces back and forth between S's, then P's, then D's, then F's, and how it does that pattern, it's just always going to go the same. It's always 1S, 2S, 2P, 3S, 3P, 4S, 3P, 4P, 3D, 4PS, whatever. I tried to do it too fast because I wanted to show off because I'm a loser. But it always goes the same. If you know the pattern, it just keeps going the same. So every problem that we do of this is basically just only going to change on how far you continue the pattern. If you understand the pattern and not just how to do the specific question, but the pattern itself, you can just go as far as you need to and then stop. So like if we were talking about carbon, for example, carbon is here, I believe. You could memorize that carbon ends on a 2p2, or you could remember that this is 1s, and then this one must be 2s because it's the second s, and then that p starts on energy level 2, and then it's 1, 2 over, so it's 2p2. I know I went through that fast. I'm going to have another example where I go through this a lot slower, but this pattern is always the same. So notice that the energy level is the first number changed for each block. I pointed this out earlier. S starts on 1, P on 2, D on 3, even though it's in the 4th row, and F on 4, even though it's in the 6th row. That's the easiest place to get tripped up, so try not to get tripped up by that. Okay, so there's a ton of different ways that we can explain this. It's an incredibly difficult concept. This is just to kind of hopefully help some of you who might be kind of struggling with what we're talking about right now make a little bit more sense. You can think of these electron and orbital levels like a house. The size of the house is based on energy level. So the higher levels is a bigger house. So energy level 1 is the smallest possible house, and bigger houses can hold more people, which is more electrons. The floor of the house that you're talking about is dependent on orbital type. S floors are the lowest, and the highest would be an F floor. Every floor then has a certain number of residents. Depending on how many rooms that you break them up to and the size of them will tell you how many people that you can fit. So an S floor or an S sublevel can only have one orbital, so it can only have one room, and that room can fit 2 people, can fit 2 electrons in that one orbital. A P floor, or I'm eating my mic, sorry. A P floor would have 3 rooms because it's bigger, it can fit more, and each of those 3 rooms can hold 2 people or 2 electrons. So 3 total orbitals, 2 electrons in each one. Same thing goes for D, same thing goes for F. This is kind of one of those concepts that you're really just going to either get it or you don't. Those of you that get it or find a metaphor or find some reference that helps you memorize it, you are going to be at a much bigger advantage. Those of you that can't, this is the best one I found. A lot of them get even weirder, even more confusing. If you don't understand it at all, go find other YouTube videos, go find something, talk to me about it, whatever. But like, this is really just a conceptual thing of you'll either get it or you don't. The periodic table is going to be your best friend, though, so try to just kind of understand what the different things on the periodic table are saying. Okay, here is going to go into these methods, and I'm going to kind of have to do a separate video where I actually go into these methods. But the ones we're going to talk about are electron configuration notation, skip through that, noble gas configuration, and then orbital filling diagrams. They're all slightly different, but they work basically the same. I do really quick in this video want to tie together these two concepts. So the thing we did last chapter and then the thing we just talked about here. We can actually determine energy held in highest energy electrons of an atom by looking at their electromagnetic radiation. So there are actually spectrums of energy that will be released. There is absorption spectrums, which is the process of an atom gaining certain types of energy. It absorbs the energy. I know it's absorb, but it absorbs the energy. And if you it's basically telling you what types of light will this atom suck in and will it gain energy from. And then emissions are if you do something that releases the energy from that atom, what will it release? What type of energy will it release? Now, type of energy could be gamma rays, gamma waves, could be microwaves, could be radio waves. We don't really care about those. For us people, the stuff that's way cooler is visible light. We want to know what types of light will metals or will substances absorb, and even cooler than that, what types of light will metals or other things give off if they are reacting, and what are they going to emit? So these look kind of like this. This is the hydrogen emission spectrum. Hydrogen, when it reacts, will have energy from those electrons that are in their little diagrams that we'll do in the separate example. Those electrons can actually jump in energy and then go down in energy. And when they do that, the energy has to go somewhere. They've absorbed a bunch of it, and then they have to release it somehow. And so what they do is they'll release energy of different levels. Remember, these are all different energy types or different wavelengths of light. The higher energies being the ones that have the higher wavelength and the lower wavelength, and the lower energy being the ones with higher wavelengths. Frequency is the key sign of whether or not something is a higher or lower energy. I don't remember if I went into a ton of detail about that, so I'm going to make sure I state that again very clearly right here, right now. Frequency determines energy. The higher the frequency, the higher the energy. So in this example here, red is the highest frequency of the waves that are released by it. They have the lowest wavelength and the highest frequency. So this is the highest possible energy that electron could release. And then down here, we've got a teal color and then kind of a purpley color and then like a more lavendery purple color. So these are lower energy. They're lower frequency and higher wavelength. And so these are going to have less energy, but they can also be released. It depends on how high the electron jumps. And so these colors will be released when you react hydrogen, basically. The most common way is by putting an electrical current through it, but in class, we're going to actually do this with fire. Now, electrons changing energy levels during these reactions. This is what I was saying here, but this is so you can pause it and you can write it down. Electrons changing energy levels during reactions can result in energy being gained or lost. Depending on the wavelength or frequency of energy, we can see a color released. Visible light is only a small band, though, so this is why you don't get to see light for every single chemical reaction. Some of them just don't do anything because they're releasing stuff that's usually either infrared, which is beyond red, or they're ultraviolet, which is kind of beyond this. Also, I totally just realized that I flipped them around. These are the highest energy levels. These are the lowest energy levels. Higher frequency is purple. Lowest energy is red. I didn't get to it until I just remembered this because the way I remember it is that ultraviolet sounds way more intense than infrared. So the lower wavelength here means that it has a higher frequency. So I greatly apologize for that. If it was any way reasonable for me to edit this video, I would re-record it. But I am almost 30 minutes into a video, and Diamond ain't having that. So I apologize. But to be very clear, wavelength, the lower the wavelength, the higher the frequency. The higher the frequency, the higher the energy. Purple is the highest energy of visible light. Red is the lowest energy of visible light. And that is the correct way to say it. I've recorded a couple videos back to back now. I apologize. Okay. So we can actually use that for another calculation of wavelength. I will also work this out in the same video. So after this, there will be a video of me working out the example of the wave equation. And then after I do that in the video, I will then work through the electron configurations. I might split that up into 3 different example problems just because it might be more convenient for you to be able to click on each one instead of having to go through and watch a full-length video if you only need one of them. So there might be 1 video after this. There might be 3. I haven't decided yet. My pointer is also frozen. Oh, it's back. Okay. But I believe that takes us to the end of section 2. I apologize for that flub at the end there. That's what I get for trying to record so many videos in one setting. If you have any questions, please let me know. If that last part confused you, I will be happy to clear it up in email or in person. Again, feel free to send me an email with anything you're stuck on. If you don't have any questions, then I hope this video helps you at least somewhat. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.